In this section we will introduce multi-layer perceptrons, which are the most basic type of neural networks. And we will do this by stacking multiple of these hidden layers. So in the last section we had this neural network which consisted of a single hidden layer, and by stacking multiple of these we will yield so-called multi-layer perceptrons. And the main reason why we do this is expressive efficiency, which means that by using multiple layers we can express the same function more compactly or more efficiently. And we will introduce a mathematical notation for multi-layer perceptrons in terms of vectors and matrices. So here's how this works. So here's again the neural network which we introduced in the last section, so consisting of a single hidden layer. So we had all these features, so our input features, which are augmented with this dummy feature, which is just constantly 1 to incorporate a bias term. So in each of these units just computed an affine function of the inputs and then applied a nonlinearity phi. And we essentially just generated this layer of units which all use the same nonlinearity phi, and they only differed in the weights. So like they are all identical, but they differed in the tunable weights we used to define the units. And now, if you look at this layer, essentially this is a layer of values, and all these. So this vector essentially goes into each of these units, and each of these units will, depending on their weight, will also produce a value. But now we can actually just stack all these values again in a vector and just pretend, well, this could now be our input. So we could actually send this through another layer and actually generate a transformation of the output of this layer. And then we could add another layer and so on and so forth. And by doing this, we will end at so-called multi-layer feed-forward neural networks, and often called multi-layer perceptrons or MLPs. So here's how this works. So we start with the single layer multi-layer perceptron, and first let's remove this output part. So now we have this input, and we produce essentially this layer of transformations. And now let's just rename this phi into phi1 because we will have now multiple layers. And now we pretend, so this was the input, and we transformed it into essentially multiple outputs into a value of into a vector of values. And now we can just pretend that these are actually the inputs and send that actually through another layer, so through another hidden layer. And we can use now a different number of units here. So for example, we could have H1 units in the first layer, and we could have H2 units in the second layer. So for example, H1 could be 100, and we would have 100 units here. H2 could be 200, and we would have 200 units here. So we can have different numbers of units in the layers. And of course, we can also use different nonlinearities. So we would use a nonlinearity phi1 here, and a nonlinearity phi2 here. And now, so by doing this and actually now having an output, sending the result of the second layer into an output unit, we would end up with a two-layer multi-layer perceptron. So we started with a one-layer multi-layer perceptron, and essentially just by sending this first layer into a second layer, we ended up with a two-layer multi-layer perceptron. But nobody hinders us to stop here, so we could just send the output of the second layer into a third layer, and so on and so forth. So just by stacking these layers and making the neural network deeper and deeper, we would get deeper multi-layer perceptrons. So, and the structure is always the same, so we always have a vector of values that serves as input to all the units in a layer. So each of these units is an affine function plus a nonlinearity, and this produces a new vector. And this vector might be, again, input to the next layer, and so on and so forth. And all the layers might differ in the number of units we use, and we call this H1, so the number of units H1, H2, and so forth. And of course, we can also use different nonlinearities for each of these layers. So this is this is how multi-layer perceptrons work. But why would we want to do this? Since in the last section, we saw that actually a single layer already gives us universal approximation, right? So we had this nice theorem that actually a single layer multi-layer perceptron is already enough to have universal approximation, which means you can approximate any function you like with a single layer already. So why would we need multiple layers? And the reason is expressive efficiency. So if we consider a shallow network, so only one layer, so this is already a universal approximator, great, but it can be shown that there are certain functions which require that we need exponentially many units. So there are function classes which can be approximated arbitrarily well with shallow networks, but it can be shown, yeah, you need to spend exponentially many units for this. And if you go to deep networks, so to multi-layer perceptrons with many layers, then it can be shown that the same function classes can be represented more compactly. So in overall, you get away with polynomial many units. So exponentially in the number of inputs or polynomial in the number of inputs. So essentially by going towards deep neural networks, you can be more efficient. So this phenomenon is called expressive efficiency. So deep networks can be way more efficient to represent nonlinear functions than shallow ones. And a classical example is the so-called parity function. So if you just consider binary inputs, so all your input features are either 0 and 1, then the parity function simply counts how is there an odd or an even number of ones in the inputs, and it can be shown that this simple logical function requires exponential size if we use only one layer. But if we make the network deep enough, then it can be shown that the parity function can be represented in polynomial size if we go deep enough. So deep networks can be way more efficient than shallow networks, and this is called expressive efficiency. And so just to give you an intuition, so these are theoretical results, and just to give you an intuition. So figure what we are doing when we are looking at a single layer neural network. So as we saw, these nonlinearities we are considering are simple, like sigmoid functions, so these S-shaped functions, or Rayleigh functions, rectified linear units, which are piecewise linear. And so figure now a real-world problem like predicting apple or pear from an image. So mapping a vector of pixels to a decision apple or pear. Well, intuitively, this is not a simple function, but like highly nonlinear. So this is like a difficult concept. And so you can figure that if you want to represent this function with just a single layer with simple nonlinearities like the sigmoid or Rayleigh functions, then you will need a lot of these functions. But if you cascade many layers, so if you have now the pixels and you transform them into a layer of nonlinear features, but then you take these nonlinear features and again transform them into nonlinear features, and then again transform them with nonlinear features. So then you can figure that even if these features are simple, that by cascading these simple nonlinearities, you can actually get pretty complicated, highly nonlinear functions. So this is just an intuition why deeper neural networks can express highly nonlinear functions more efficiently. So this is the upside of deep neural networks, so they can be more efficient. And there has been a traditional downside of deep networks. So they used to be harder to train. And this kind of led to a neural network winter in the 90s and 2000s. So as mentioned in the history overview, back then kernel methods and support vector machines were way more prominent than neural networks. And the word on the street back then was something like that, oh, neural networks which are deeper than 2 layers cannot be trained. And essentially this had mostly to do with the nonlinearities people used back then. So these sigmoid units were prone to gradient diffusion. So like essentially they saturate, and then the gradient, so the derivative, which is used for learning, which we will discuss later, essentially just stalled learning. And so the deep learning wave, which essentially started in 2006, introduced a lot of tricks of the trade to actually enable training of deep neural networks. And neural networks can nowadays be scaled to hundreds and even thousands of layers. So really deep neural networks can be trained nowadays. Here is again a multi-layer perceptron, and we will now introduce a vector notation for multi-layer perceptrons. So neural networks are really complicated things. So we have all these inputs and we have all these units, and so this really tends to be complicated. So let's use a more compact notation. So for notational sake, assume that we have L hidden layers. So here in this example, we have 3 hidden layers. And let's denote with H underscore index the number of hidden units. So H1 is the number of units in this layer, H2 is the number of units in this layer, H3 is the number of units in this layer, and so on. And if in general we have L hidden layers, and we might have different number of units in each of these layers. And as explained previously, so each of the edges in the neural network is equipped with a weight. And in order to make some sense in the notation, so we will denote each weight with a W, and we will have 3 indices. So we will have the superscript I, and we will have a first subscript K, and we will have a second subscript J. And the superscript denotes the layer of where the weight sits. So for example, if the superscript I is 1, then we are talking about these layers, and we are talking about the weights which sit on these edges. If the superscript is 2, then we are talking about the weights which sit on these edges. And if I is 3, then we are talking about these weights. And 4 would talk about these weights. And so this is the superscript. This index is the layer. And at the subscripts, so K denotes the unit from which we get input, so from where we come, and J denotes the unit where we go, so where does this weight feed into. So if we look at an arbitrary edge, for example, this one which starts at the dummy index and goes to the last unit here, so this would be, then K would be 0, since the dummy unit has index 0, and J would be the number of units in this first layer. Or, for example, if we look at this weight here, so this weight would have a layer index 2, since it's sitting in the second layer. It would have K index 1, because it comes from the first hidden unit, and J index 2, because it goes to the second unit in the next layer. So this is the indexing notation we are going to use for the weights. So this is how to address the weights in our neural network. And now let's go to the ith layer, for example, the second layer. So I is 2. And let's look at the jth unit. So for example, the second unit. So I would be 2, which means we're in the second layer, and J would be 2 because we look at this unit. And now, so this unit here gets a lot of inputs from the previous layers, so these edges here. And let's just collect the weights which sit on all these edges which go into this unit into a vector. So we have this dummy, so that the bias term coming from a dummy unit, and then we have all the weights which come from these previous units here. So all the weights which go into this unit are now collected in this vector, and this is indexed with I, second, so I2 means second layer, for example, and J2 means second unit. And if J is, for example, 1, then we would talk about this unit. So we're collecting all the ingoing weights into a vector, and we call this vector Wij. So ith layer, jth unit, and these are the ingoing weights. And now, so all the hidden units compute essentially features of the input, but there's actually no real difference from the actual input. So we can actually define the first input, so that our actual input features we could define as the 0th hidden layer. So we will define H0, so the number of hidden units, so to speak, as D. So this is actually the number of features. And we'll also comment it with this dummy feature, this one. So we're just collecting this vector here. This vector here is now called H0. So we just collect all the inputs plus dummy index in H0. So this is this first vector. And we will also collect all the hidden units in the higher layers into vectors, into vector Hi, where I is again the layer index. So for example, I1 would collect all these units here into one index, here into one vector, into this vector, plus a dummy index. So we've now collected this in a vector, and we've collected these units in a vector, and these units in a vector, and these units in a vector, and so on. And now let's again look now at the ith layer and jth unit. Recall that each unit just computes this affine function. So this linear function, so this already includes the dummy term, this ones, which respects the bias terms. So it's just a linear combination of the previous hidden units. So here these are the hidden units of the previous layer, I minus 1. So we're talking about the ith layer, and I minus 1 is all the hidden units from previously. So if I is 2, we are talking about this layer, and then I minus 1 would be the outputs of this layer. So this is the activation for in the ith layer and jth unit, and then you know the output of the unit is actually just applying this nonlinearity. But now if you look at this here, this looks familiar. So we can just write this as a vector, as an inner product. So this is just the definition of the inner product between the weight vector of ith unit, ith layer and jth unit times the vector of all the outputs in the previous unit. So I minus 1 might be, so if I is 2, then this would be the vector of outputs in the previous layer, and essentially the activation for this unit is just this inner product here. So this activation can be compactly written as this inner product, and now the hidden unit is just applying this nonlinearity to this inner product, so to this IAJ. So again, so the activation in ith layer, jth unit is just a inner product between the weight vector and the vector of previous outputs, and the output of this unit is just applying the nonlinearity. So now we can go further. So we have first packed all the weights for ith layer and jth unit into a vector, but we can now take all these vectors and pack them into a matrix. So we pack them now into an hi minus 1 times hi. So this is the number of hidden units in the previous layer. This is the number of units in the current layer. And we pack them into a weight matrix W superscript I. So this is the weight matrix for the ith layer. So by just packing these vectors here as the columns of this matrix, we get now a weight matrix Wi. So essentially if I, for example, is 2, then this W would just describe all these weights which sit on all these edges here. And we can now also collect all the activations. So we saw the activations is just an inner product. So we can collect all the activations in the ith layer, jth unit. So we run over J and pack them into a vector. So here we run over J, J1, J2, and so on, and so on. So we collect all the activations into a single vector. So these are all the activations in the ith layer. And now it's easy to see. So the first element is actually just this vector times the previous output. And the second activation is just this vector times the previous output, and so on. And the h-ith activation is just this vector times the output. But this just means that all the activations are just given by the weight matrix transposed times the output of the previous layer. So now this is just a matrix vector product. And so we can get all the activations with a single matrix times the output vector of the previous layer. This is the vector of all activations in the ith layer. And if we apply now the nonlinearity, so element-wise, so phi I now acts element, so if we apply phi I on a vector, recall that phi I is actually R to R, so it maps number to number. If we apply it to a vector, this just acts element-wise. So again, the activation on the ith layer is actually just given by matrix multiplication of the weight matrix in the ith layer times the output vector of the previous layer. And if we apply phi I element-wise, we get the output of the current layer. So this is so essentially all what the multi-layer perceptron does is matrix. So each layer actually just applies a matrix multiplication plus an element-wise nonlinearity. So again, looking at this neural network, and it's very complicated, but in mathematics it's actually very, very simple. So all what happens is that we have a weight matrix here, W1, W superscript 1, so this weight matrix here. And all what happens is that we take this vector here and multiply it with the weight matrix W1. So W1 transposed times the input vector gives us the activation for the first layer. And we call this A1. And so to this A1, we apply the nonlinearity phi1, element-wise. And this is the output. So this essentially is the output of the first hidden layer. And now we are looking at all these weights, and they are just collected in a big matrix W2. And now the activations of the second layer, so this A2, are just this matrix times the output of the first layer. And now we have the activations of the second layer. And if we apply these the nonlinearity phi2 to these activations, we have the output of the second layer. And now we consider the third layer, which are actually just again collecting all the weights into a matrix W3, and W3 transpose times the output of the previous layer is now the activation for the third layer, A3. And then we apply phi3, and we get the output of the third layer. So this is up to here. And then we have essentially just these weights here, collecting them into a matrix W4. And again, so just by multiplying this matrix with phi3, we got the output. So you see it's an extremely regular structure. It's always so input, matrix multiplication, applying nonlinearity. And then we just repeat. So this is now the new input times matrix applying nonlinearity. This is now the new input times matrix applying nonlinearity. And finally, we multiply with a matrix, and this is the output. So in general, this final matrix, so this W4, the output matrix here, is in general HL. So this is the number of hidden units in the last layer, times O. And O is the number of outputs. So here we see O is just 1, because we have only one output. But in general, if we have a neural network which has multiple outputs, of course, this O can be larger than 1. Then we would have like multiple units, and each of them would be just a linear combination of these the outputs of the last hidden layer. So in this way, we can write a 3-layer neural network in one line, namely in this line. Extremely regular, just vector times a matrix, nonlinearity, times a matrix, nonlinearity, times a matrix, nonlinearity. So it's just a nested, alternating nested arrangement of nonlinearity and vector matrix multiplication. So this concludes this section. So multi-layer perceptrons are essentially just the extension of this single-layer neural networks. Just repeatedly treat hidden layers actually as new inputs and apply another hidden layer and another one. So this yields multi-layer perceptrons. And we saw that, so we argued that deep networks can represent certain functions more efficiently, so you can get away with fewer neurons and fewer parameters if you go deeper. And we introduced this vector notation. We saw it's just nested matrix multiplication with a weight matrix and then applying a nonlinearity and repeat. So this is just a nested function.